Okay, this is our module 06, which is under synchronization. Last class, we have discussed several related to synchronization. Okay, I already inform all of you, like there is things we take a look, like what is the background, how the problem will be a cure, especially when we talk about the rest condition. And later on, you're going to look also in terms of deadlock. So this is under a background. And then we take a look into a critical section problem in also touch about introduction and how our problem will be a cure. And later on, we look, there will be several methods for us to solve the problem. So last time in our previous class, we already touched on a background. There is a two, so we do some recap first. If you still remember, wait. Okay, sorry. Let's continue. Okay, there is two process only that you need to know to differentiate between independent and cooperating process. So last time I did briefly discuss with all of you what is independent process and what is cooperating. So by having these two processes, you need to know how to differentiate between these two. This one is quite easy because you know already the meaning of independent and you know already the meaning of cooperating. So by these two terms, you can also know the keywords. What is the things under independence and under cooperating process? Then you know also that it will be a cure a rest problem when, if you still remember, when they are processes try to access the same data. So let's say you have the global data that sharing about name, let's say. So your data is stored into your CPU, of course, your memory. So you have two process 1 and process 2. When these two process try to take informations or try to access the similar data at same time, which is synchronized at the same time, let's say 20 seconds, so it is also 20 seconds, try to grab the data, which is more than one process, if the minimum of course 2, so it will be occur a concurrent access, especially when you want to share data, may result in a data inconsistency. So when you try to fetch similar storage data, and then we can conclude it. So there will be a rest condition. After this, you will also touch what and why rest condition will be occur. So the synchronization mechanism is usually provided by both hardware and also the operating system. So there will be a illustrations of problem, the problem consumer problem, basic consumer, which is about atomic last time, in terms of load and store instruction. Okay, there are two processes maybe, which is when you why rest condition occur, which is executing simultaneously. If let's say it is like 1 p.m. you try to grab a data at the similar time, which is simultaneously, so it can occur a rest condition. Trying to access a global variable, same global variable, same data, so this will be also give a point why rest condition will be occur. Next, this one we have example last time when you try to execute chain equal to get char, which is you try to access same time at a chain get char for both P1 and P2. When you have P1, you're going to try to execute this. Of course, you're going to enter this code. But at a similar time also, you will try to run also P2. That's why it will be interrupted by P2, and P2 will enter this code. So your value will be changing. That's why when you try to resume P1 back, your initial character value also will be different. So last time we tried to look into back this statement just for example condition. When you have two processes, you try to execute the similar global sharing data. So it will be occur for you rest condition. And if you look into, there is two keyword last time, which is about the process. When process must be prevent from entering a section, D is also known as a mutual exclusion, and also the keyword of critical section. So you need to remember these two keyword. And under producer-consumer problem, several processes work together to complete common tasks, which is process cooperation. Okay, this is called as a process cooperation. Common paradigms for cooperating processes. Process produces information that is consumed by consumer. So I don't know, I already forgot whether we already touched or not about process and consumer, but just recap, there will be something in between producer and consumer. So between producer and consumer, you need to also remember the correlation. Producer will be plus the counter, and the consumer will be deduct. So let's take a look into what is the correlation between consumer and also producer. And if you still remember, I guess we already touched because last time we just focused on module 6. So we have two meanings, which is unbound buffer and bound buffer. For unbound buffer, of course, when you have this keyword, you know there will be no limits. There is no limits, which is, it is a free for the size. Unlimited buffer size. You can have until infinity. So it's depend, there will be no range at all for unbound buffer. While for bound buffer, of course, if you have this keyword, you know it will be have a limit or a range. Here is the correlation between producer and consumer. And there will be three things here, which is example of full buffer, partial empty buffer, and empty buffer. So let's say here you have altogether 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 buffer. So let's say if you are this is full, the data here feed in by producer is full. So producer cannot put in others information. That's why you will look into later on, producer need to wait if buffer is full, because you cannot fill in anymore. Okay, last class we already touched. I still remember this. Okay, producer need to wait if the buffer is full, so you cannot fill in. Actually, you're going to fill in one by one. From empty, producer will fill in one section, one buffer. It will fill in another one. It will fill in until half or partial. And then after that, it will fill another. In a similar time, after producer fill in, consumer can take the information. Can take the data inside. That's why you can see sometimes there is a partially empty buffer, because consumer also already grab information here, grab the data. That's why it's empty. When it's when buffer is empty, consumer need to wait, because there is no and nothing here for consumer to grab, isn't it? So that's why there will be a condition where consumer needs to wait if buffer is empty. So here is the example, and the most important, you need to remember outbound buffer, bound buffer. And here is example, which is full buffer, partially empty buffer, and empty buffer. So there is also things under producer and consumer that you need to know, which is procedure put data in one slot. So you're going to see producer will put data in one slot, so it will fill in, while consumer retrieve data from another slot. So if there is another slot that having a data, it's going to take it, because you cannot in similar time doing it together. So it will be take turns if procedure will put and consumer will grab. But if it is simultaneously happen, it's going to be different slot. One slot is putting by producer, so consumer retrieve from another slot. So consumer will retrieve from here. And producer and consumer need to be synchronized so that consumer will not retrieve data before producer put in data into buffer. So this one and this need to be synchronized and know each other. Because you can see here before, let's say this is an empty slot. Supposedly, procedure will be put in data first. But if there is no synchronization, consumer will try to grab data from here, but it's empty. So there is no synchronization. If it should be synchronized whereby if procedure, okay, let's say here is a slot that already filled in. So consumer know and it synchronized that it's already putting in the data, so it can grab the data here. If this slot before procedure tag and put the data in, so you cannot retrieve data. That is very simple process that you need to remember. Here is the general program that you can use to write in terms of producer. After this, you're going to continue with a consumer. So here you can see here, you are using a while. If it is true, of course, produce item in the next process. So you're going to use a counter equal to buffer size. So it's depend also about the size of buffer. It will be also similar also with the counter. Let's say here our counter now at equal to 5. So your buffer, let's say it is already point to the buffer 5. It is also depend on size. If the maximum size of buffer equal to, let's say, 7, so you have altogether 7 slot. And counter, let's say, at 5, so you are here. There is another 6 and 7 left. So there is a correlation between counter and buffer at your program, depend on where you are pointing at. And buffer in next procedure produce. And then you can see this is the important part, which is counter plus 1. You're going to add on the counter for a producer, and for the consumer, you're going to deduct 1. So that is the differentiation between producer and consumer. It will increase and it will decrease for consumer. So here you can see in terms of bounded buffer problem, there will be a problem. So we just talk first, we just talk about problem, and later on we're going to see the solution. So share variable here in our counter buffer, initial values of for in out equal to counter equal to 0. So you need to note initial value for in out counter equal to 0. So both routines are correct in executed independently. However, it may give problem if run concurrently when the processes are not synchronized properly. So here will be give you a problem when run concurrently when the processes are not synchronized. Okay, here if you have the total size of buffer equal to 6, and at the time, let's say at 10 a.m. in the morning, your current counter equal to 5. So there will be also a statement later on when the counter will be increased for a producer and consumer will be decreased. Here you're going to see that the counter may be 4, 5 or 6. 5 is the current one. Producer will be increased. Consumer will be decreased. You're going to have different counter value. So you cannot have this. This is going to make a problem. The correct value is 5. If it's synchronized properly, you're going to have 5. So let's see. Each statement consists of several mission instructions. So here is under producer, here is consumer. So supposedly you're going to see, you're going to update your register, and then when you're going to continue later on, the total counter value, it will be different and etc. So here is the example why and how it's going to be occur the rest condition. When you have of course you need to run the program. So when you have this register 1 for producer, register 2 for consumer, register 1 equal to counter for the start, you will assume it to be similar to counter, and you know counter value is 5. Okay, let's take a look here because it is initially equal to 5. So register equal to counter, register 1 at 5 for the first indicate instruction. After that, producer will be doing the second one, register 1 equal to register 1 plus 1. So here is the value, register 1 is equal 5 now. So when you plus 1, it's going to be 6. So register 1 now already become 6. And your consumer will be as a process 2. It will be try to interrupt your producer. So when it became like that, without you doing an update before that, so register 2 will be took place. So you can see here, it will be register 2 equal to counter. So here your counter before this is 5. And you can see there is no instruction at all to update your counter value. So that's why counter still 5. And register 2 is equal to 5. Used for this instruction. So second one, register 2 will be decreased. So 5 minus 4 is become 5 minus 1 is become 4. So register 2 is equal to 4. And you can see here there is a conflict where you're going to have counter equal to R1. And then suddenly it's all update also after process 4. It's update. Okay, for now it's 6. Okay, of course it's wrong because supposedly counter is equal to 5. But let's see another line. Counter equal to register 2. Register 2 is 4. So if this is the final, it's not going to be similar. Because supposedly for the final one, you need to have the similar counter value. If not, it is a rest condition. Okay, so it is a synchronization problem, occur a rest condition. After this, you're going to see how to solve this problem. Okay, the rest condition definition, you can try to read by yourself. There is two definitions, and we also last time already discussed. And how to solve a rest condition. So, to solve the rest condition, ensure that only one process at time can manipulate your share variables, which is your counter. Therefore, process synchronization is needed, means that coordinating the activities of two or more processes. You're going to look into the solution. How to solve? We need to make sure that the executions of these execute and atomic actions, which is going to be one in one time. That is, while it is being execute, no other instruction can be executed concurrently. So similar also for counter equal to counter minus 1. The ability to execute an instruction or a number of instruction atomically is crucial for being able to solve. So here is the similar example as last one, which is that the problem, isn't it? So we give you a solution, which is producer should update the counter, you can see here, before the consumer read the value. Before the consumer read value, you can see the difference at T2, here, and this T2. What is the difference? Last time we did cover in our previous class. So here, before your consumer took place, you need to update counter equal to register 1. So when you update, this is the solution. You need to update first. Your consumer need to update the counter. Then you're going to see your register will be equal to 6. Then you're going to minus the register. So it equal 5. And lastly, consumer. And you can see the final counter is equal to 5, which is equivalent to initial value of the counter, which is equal to 5. So we solve the rest problem. Okay, so that is a solution, one of the solution, of course, if there will be a rest problem, a rest condition. So now we're going to see also there is a critical section problem, whereby if you have something here that you want to enter, last time I give example like going to open house, or your friend, I don't know, open house like all can join together, I think it's gonna, or maybe to your friend house, which is very small house, you cannot take more than one guest in one time. So that's why you need to ask the permission from your friend first. Can I come? Is there anyone in your house? So you need to ask a permission first to enter. So we assume it as a critical section, CS. If someone want to enter CS, you need to ask first and only one guest in one time, which is one process in one time to enter the critical section. So let's say a part of program which is segment of code for each process, and there is a several process. Each process has critical section segment of code. So process may be changing common variable, updating table, writing file each. When one process in critical section, no other may be in critical section. So this is very important. So only one process in one time inside your CS. Inside your CS. So critical section problem is to design protocols to solve this. Each process must ask permission to enter critical section in entire section code. So then after you already request, you're going to enter. After enter, you're going to execute or exit. Where you're going to exit, you're going to exit and go to the RS, which is reminder section of the code. Okay, so you need to remember the flow. First request or you send the permission. So first request or send a permission to enter. So you're going to enter the CS. After you enter, you're going to exit. Where you're going to exit, you're going to exit to RS, which is reminder section. So this is the general structure of process when you want to enter critical section for each process. So you're going to use this general structure for your program. So here CS, process structure. A process, let's say A, process A, you try to go to the CS. And at T2, suddenly there is a process B, try to also. So you request first, you ask a permission, and then you enter. So when you enter, before you finish, you cannot say to your friend, dah berhenti makan, you stop eat. You need to go because there is another guest want to come to my house. You cannot ask them, right? So that's why when there is someone guest at house, so you need to wait for your friend to finish it, to finish their process first. So you will say to another friend, okay, wait in the car. Just wait. So you block them. Don't come to my house because there is a guest. So you need to wait until this friend go back or go out first. So you cannot like, okay, this one is ready to go out. Okay, you can enter. No, you need to wait this friend to go out first. Of course, after that, you're going to prepare. And then another friend can come and enter. Of course, this one will ask request a permission also at this type, and at these two it will be try to attempt, try to enter, but there is someone in your house, so you cannot ask them to enter. So you said wait, so it will be blocked. After leaving, after this guest go out or exit, then your another friend can enter, which is process B. Enter your critical section or region. And then it's similar process. B will be leave, and let's say there is another process C, you can enter the CS. If it requests before that in the middle, you cannot also give a permission, it's going to be blocked. So there will be several algorithm per process. Enter section to critical section is to disable this interrupt. So you're going to disable, which is you cannot have any interruption. When you already exit, then enable instruction, which is another person can come in. So implementation issues for this algorithm, which is uni-process system and multi-process system. When you have uni, so currently running code will be executed without preemptions. For if you have if you are using a multi-processor system, Generally, two inventions of multiprocessor system, operating system using this not broadly scalable. So, is this exception solution? This one also we already take a look. So let's see how if we have several process. So for this algorithm, you need to know there will be only two process. If you have only two process, then you can apply. But before that, just take a look into the general one using a variable turn to indicate what is the next process. What is the next process? Algorithm is correct, only one process at time in the critical section. So there will be a requirement for a CS solution. You need to make assumption. You need to make assumption in a CS solution. First assumption, assume that each process executes at non-zero speed. Second, no assumption concerning relative speed of n process or numbers of CPU. The algorithm does satisfy the three essential critical to solve the CS problem. So here they are. The algorithm satisfied three essential criteria, which is mutual exclusion, process, and bounded awaiting. So last time until here only we look into. So now we look in deep. So solution to critical section problem, which is you need to satisfy these three requirements: mutual exclusion, progress, and bounded waiting. So from all this problem, you're going to have four altogether as a method or approaches for you to solve CS problem. First, software defined. There will be several software defined to solve CS, but in OS subject, we will look into a Peterson's only. Okay, you need to know there will be several, but we look into Peterson's for operating system subject. Second one, hardware support. There will be two type of hardware support to solve a CS problem, but we will only cover test and set. And another one, support from the operating system, or in a short form we call as semaphore. And lastly, support for programming language, which is other Rendezvous, but we're not going to look into this module 6. So what we will cover next in our next slide, which is Peterson, test and set, and semaphore. So let's take a look directly for the first one, which is software defined under Peterson solution. So good algorithm software solution to process solution, which is assume the load and store machine language instructions are anatomic. You know the meaning anatomic, you can only run one process at one time. So the two processes share two variables, integer turn, boolean flag. The variable turn indicate whose turn is to enter the critical section. So that's why later on you're going to see Peterson solution only two process. If you have P1, P2, P3, you cannot use. You only use if there is a two process that going to try to go into a share variable. So here you're going to have algorithm for process, which is flag I equal to true. If this statement, it means that this process is ready to enter. Let's say you have P1 and P2. If this is flag 1 equal to true, means that P1 is ready to enter the CS for this line. For second one, turn equal to J. So you need to have only 2, right? So let's say here, turn equal to 2. If, but you can see for the first time, it said, okay, P1 is ready to enter CS. But then, for the next line, but if P2 want to enter, so let P2 enter CS first. Okay, for turn equal to 2, so means that, okay, just give P2 to go to the CS if your turn equal to 2. And while flag 1, if let's say, so if you have meet these two conditions, if flag equal to 2 and your turn also 2, then you're going to go to the critical section for the P2. So for this one, flag equal to false means that flag 1 equal to 4. It is I'm going to exit, or I'm not ready to go to the CS. So this is the general algorithm or program that you can use for the structure process. Later on, you're going to see also this example again. Proable that the 3 CS requirements are met, which is mutual execution, progress requirement is satisfied, and bounded waiting requirement is met. So let's see here when we have two process. Rewrite the Peterson algorithm for CS solution and also for the process 1 and 2. So here is the solution. You can see here if you have 2. First, at the process 1, we call as P0. If it is true, then turn equal to 1 because this one, okay, P0 is ready. But you need to check, is P2 is want to enter to CS or not? If it's want to enter, so you're going to see flag 1 and turn 1. So do nothing because P1 will take place. But if it is false, you're going to go to the reminder section. So try to read this, how about the flow, but this is the most important about the definition for each program. So I am ready to enter CS for P0. But if you execute, if you want, but you can execute your own CS for P1. It asks, if you are ready to enter, it's your turn and I will wait. So P2, P1 will be enter and P0 will wait. Otherwise, if you don't want, then I'm going to enter CS. Lastly, flag 0 equal to false, which is I don't want to enter CS anymore. So when you understand this basic program, so it's easier for you to have to play around with this program depending on the process. So there will be a several exercise. Last time we want to discuss together. So under exercise 3, so that for this exercise 3, if you were given with this table, going to have several true, false, depend on this program, okay? Because this is the general that you're going to play around. What is the event that happened at that time? Imagine if you have only these two process, which is P0 and P1. At initial one, if let's say flag 0 equal to true, flag 1 equal to false, turn is equal to 1. If you still remember here, let me bring the code beside. Okay, let's say here you have P1 and P2. Flag 1, flag 0, it is true. What is the meaning by this? Just now I mentioned. Means that P0 is ready to enter CS. Flag 1 here is false, means that it is not true. So turn equal to 1 means that, okay, supposedly it's going to give to P1 to enter. It will check. P1 also want to enter here, but when you check, flag 1 is false. So you're going to check whether you're going to have flag 1 or not. Okay, P1 is not ready, but here you just check. If you want to enter, then you can. Means that P0 give a permission for P1 to enter CS first if flag 1 is true. But now flag 1 is false. Means that P1 is not ready to enter CS. So what will happen is just here at the first one, P0 request to enter CS. Because P1 is not ready, P0 will try to enter CS. Similar one, after it requests, this is the similar condition, because of course you cannot directly enter. I remind you again, there will be a several after you before you enter your CS, you need to request. After you enter, you're going to exit and go to the reminder section. So at this T1, what happened? P0 enter CS. After that, the changes on the condition. You're going to see this true, and now flag 1 or P1 mentioned, okay, I'm ready. I'm ready to enter CS. But before you can enter, before you can send a request before you enter, this P0, you need to exit. But before it's exit, you can see, because I still here, I still inside this critical section. So P1 will request, because it said, I'm ready. So it's request to enter CS. Then what happened? It just request and waiting unless this one change to 1. Because you can see here, if this change to 1, then P1 will enter. But it mentions it's 0 here. So it's not going to look into this part. Which is at this line, what happened? At this line, it will say, okay, if P1 want to enter, then I give you. But this one, I don't want to give if it is 0. So you can see here, turn is 0, turn is 0. That's why it's not going to consider P1. Just ask P1 to wait until I go up myself. So it is false here, means that at this one. I'm going to exit. After I exit, I enter reminder section. So first, I'm going to execute RS, which is go to the reminder section. Next one, similar condition. After I already execute RS means that I already go out from CS. So P1 can enter now. P1 enter CS. What is the next condition? Similar one. So nothing happened means that P1 is inside CS. P0 will still continue execute the reminder of RS. Next, now I see that P1 also want to exit. See, P1 also want to exit. So P1 will execute RS. What else? So if it is still similar, so these two will take place, which is it will be continuous. P0 execute RS. And lastly, if there is a conditions of here, it's true now. You can see? So then it shows, okay, P1 is ready to enter. Before it's enter, it's need to send also request or permission. It will be continue. So please try to do a next exercise, continuous exercise from previous example. And this is the Peterson algorithm after we summarize it. Okay, so after this we will continue after we take we're going to take 5 minutes break. After this we're going to continue with the synchronization hardware. So here we already cover our Peterson. After this we look into how we're going to solve it using a synchronization hardware. Is it okay? So let's take a 5-minute break. Then we're going to continue after this. Okay, class, let's continue with our module 6. Is it okay? So let me start.
Yes, better.
Okay, thank you. So let me start here. Under solution to critical section problem, we're going to use another method, but now we're going to use a log, using a log. So software-based solution like Peterson's are not guaranteed to work on modern computer architecture. Just now, you already look into the Peterson, right? Many systems provide hardware support for implementing the critical section code. So a solution is ideal using a locking. So this is the code that we're going to use after this. Okay, after this we're going to use using a locking. And why we want to have a solution using lock instead of using turn. This one is using turn, using a partition. So you're going to see this one, where is the, okay, using a turn and also flag. Now we try to look into deeper using the log. And because of partition having disadvantages, just now I already mentioned, right? Only 2 process. If you have 3, you cannot use this partition. Okay, let's say P1, P2, P3, you have 3 process. So you cannot use partition just now. It is just only if you have 2 processes. And it's involved busy waiting. Buka. Okay, we're going to look into synchronization hardware. Modern machines provide special anatomic hardware instruction to implement lock, which is anatomic non-interruptibles. 2 type instruction: test memory words and set value. Swap contents of 2 memory words. Let's see here under test and set instruction. If you still remember, it's give you an last time, where is it? Wait, I go back first. Okay, you have test, set, and swap, but we're going to look into test and set for hardware support. And 2 type instruction: test memory words and set value, and another one is swap. 2, yeah. Then we just look into test and set instruction for DCS. Test and set is single indivisible machine instruction, known simply as TS, and was introduced by IBM for its multi-processing system 360, 370 computers. In single machine cycle, it tests to see if the key is available and if it is set to unavailable. So test to see if the key is available, and another one set if it is unavailable. So you only have to test. Where is it? Test if the key is available and set if unavailable. So you still remember the L subject. If set is equal to 1, so it's going to be set. If unavailable means that 1, if it is busy or unavailable. Okay. And test, just test if it is free, it's going to be 0. So first, you're going to test whether it is available or not. If it is unavailable, you're going to set. Set, if you still remember under DL, is going to be equal to 1. So that's why if it is unavailable or busy, it's going to be 1. Otherwise, if it is free, then it's going to be 0. So this is the important condition for you to remember. So you're going to have general program as usual in your TS, test and set instruction. So you're going to have boolean test set, and then you're going to have equal to target. If a target is true, then you're going to return RV. So properties execute automatically, return the original value of pass parameter. Set the new value of pass parameter equal to true. So a way and how we're going to apply this test and set for CS application. So a process 1 will test the condition code using test and set instruction before you enter CS. Of course, whenever you want to enter something, you cannot just directly enter. Okay, so you're going to use the code using test. If no other process wait in the CS, then P1 will be allowed to process and condition code will be changed from 0 to 1. So you can see here the flow. First of all, by using a test and set, you're going to also use let's say you have P1 here. You're going to use a test condition code using test and set instruction before enter. So this is the first one. Second, if no other process in CS, if you check, okay, CS is free, your friend house is free, then P1 will be allowed to process the condition code, which is you're going to go enter. It's going to be 0 to 1 because just now is free, right? 0 is equal to free. So first you're going to have 0. When P1 is enter CS, it's going to change to 1. So means that, okay, my house have someone. I have guests in my house. Cannot enter. So you just give a flag ataupun signal, or it is a signal for others process. Okay, I cannot enter because someone is inside. Later P1 will be exit. Of course, you cannot stay forever in your friend's house. So you're going to exit. The condition then reset back to 0. So others will know, okay, dah tak ada orang, you can come to my house. It's free already. So the others process can enter CS because no one is at the house. On the other hand, if P1 find a busy condition, if let's say you want to go into the CS, you want to go to the CS, but when you say, it is 1, means someone is inside, it is a busy condition, 1, right? Unavailable. Then it is placed in waiting loop. So you just need to wait until someone in this house exit or go back. Then you still need to wait. Where it is continue to test. You will always keep asking your friend, this one has already go back or not? And then at 5 minutes more, you ask again, your friend already go back or not? So you always ask your friend, and it's mentioned as a continuous test. The condition until your friend said, okay, dah balik, you can come in. So that will be happen. So solution using test and set. Just now is the general condition. So share Boolean variable log indicate a false log equal to 0. This log just now we look into. And each progress wishing to execute CS. If you have at least 2 or more process want to enter CS at the similar time. You only have one small house. You cannot ask your friend P1, P2, P3 to come together. So this will be execute. Solution result is busy then waiting. What about bounded waiting? So, however, this algorithm does not satisfy bounded waiting because you have like limitation. Let's say, okay, this is your friend house. Okay, what happened is, your friend said, okay, I have open house, but your open house is not a really open house because you have a very small house, which is only limit one guest at one time. But where is the bounded? Where is the bounded? The bounded is mentioned, okay, my open house is only from 10 a.m. until 11 a.m. So let's say P1 is entered already. So enter already, and then you don't know how long this P1 will be at your house. You cannot say, okay, go back. You cannot write. So you don't know how long. So it's going to be a problem. So that's why it's not satisfied if you have any bounded. It's unlimited, it's okay because you have a unlimited, and then after that P2 can enter. If let's say P1 until 10:45. Then 10:46, your P2 is entered. So P3 cannot. So it will be a problem if you have a bounded waiting. So you can try to look into the answer. It's our extra notes I provided, textbooks. So you can see what is the solution in these pages. But you need to know that we're going to use the log here for the test and set to check the conditions and stuff. So here, so here is under our test and set condition. So you're going to go and to look deep in reading for pen saya tak keluar. In the 210 until 212. So let's take a look directly to mutex log, the next algorithm, which is previous solution are complicated and generally inaccessible to application programmers. Just now for hardware. So now for the application program. So OS designer builds software tools to solve CS problem. Simply tools is called as mutex logs. Which using this mutex log, it has a Boolean variables which is available. Associated with it is indicate if log it is not available. So it is whether available or not. Just now for the hardware, you can see test and set. It is a whether it's free or not, right? So now available or not. However, there is more robust tool that you can have similar to the mutex log, but also provide more sophisticated way to process the synchronize. So you just need to know there is a mutex logs, but we're not going to go deeper in mutex logs. This is just for you to know how mutex log will be using. And lastly, our last algorithm, which is semaphore, a method of visual signaling usually means by a flags or a light. So they are used in railway. So let's take a look. You can read it. Example here. Okay, this example. Now you can see here. If you want to give a sign, okay, semaphore means you are using a visual sign. You not give like I don't know what is the Barbasa, but it gives you in terms of visual sign means using a flag or a light. So this is using, I think a flag, we can call it as a flag, but you can see also that this one is also using flag. But if you have a light, like a traffic light also, it is using as a traffic light. So here, it is not light, but you can assume it's to be stop, red light, and this one is clear as a green light. So semaphore is using a visual, something that you can see, whether it available or not, or maybe you can pass or you can go into the CS or not. So in terms of trails, you can see here the example. Similar in our OS, signal if when a resource is free. Free means all clear and can be used by a process. So semaphore in OS, protocol mechanism for task communication. So where is going to apply? So specifically, semaphore are used to control access to share memory, share resources. Second, signal the occurrence of event. And lastly, allow two tasks to synchronize their activities. So this is the use of semaphore in your OS. So synchronization tools that provide more sophisticated way compared to mutex log, which is your semaphore, for processors to synchronize their activities. Semaphore we use as integer variables, can only access via two indivisible atomic operations, mean that only two process also. When one process modify semaphore variable s, then another process can modify the variable. Then no other means that the atomic also. Concurrently, mutual exclusion. Wait and also sign. So last time originally we call as P and V in your dot algorithm. So P is equal to provariance, which is similar to wait or to test, and V Verhoeven to signal to increment. So how you're going to apply this semaphore in terms of weight and also signal? You have to separate, which is when you want to wait. You want to wait operation equal to P, whether it is P1, P2, it depends on your progress process. Wait S while S less or equal 0 means that it is a busy waiting. You're going to execute S equal to S minus 1. Where your semicolon after this, of course you know a comment. The code start while your S equal to 0. Then code will be resumed when S is non-zero. Of course, if non-zero, then you can resume back. So S implied a busy in your critical section. I'm not available. There is a guest in my house. Process waiting. Operation must wait until s more than 1 or a positive value before going into your critical section. So this definition of signal operation equal to V also. So sign S equal to S plus 1. So similar, you can see you're going to request, you enter, and then you're going to execute the RS. So there is a note here, S equal to 0. This implies that there is a process in critical section. You have several types of semaphore. Counting semaphore, binary semaphore, which is similar to mutex, while counting semaphore integer value can range over an unrestricted domain. So can implement a counting semaphore as a binary semaphore. So this is under semaphore usage, where and how you're going to apply your semaphore. You can solve various synchronization problems using semaphore. A solution to CS problem, going to create a semaphore synchronize, which is indicate to 1. 1 is what? You're going to wait. Wait to syncs. And then later on, you're going to see there is a somewhere in the critical section, and you're going to signal whether it is a 0 or 1. Using this general code for our semaphore usage. There is a example for semaphore under semaphore usage, which is example 1, example 2. Later on, you're going to have also exercise. You can try to do it for the exercise. We will discuss later on in the I think next week. I'm going to provide you with a video for the semaphore example 1 and 2. Let's take a look into semaphore implementation under busy waiting. Must guarantee that no two processes can execute, wait, and signal on same semaphore at same time. So you know already, if you use and do a similar or synchronized process P1, P2 at similar time, it will be a problem. So this is always a TNC for all the algorithm. Thus, the implementation become CS problem. We wait and signal code are placed in the critical section. This implementation is based on busy waiting in your critical section. That is code for wait and signal. So here, but implementation code is short, little busy waiting if your critical section is rarely occupied. So take a look at this question. You try to look into your textbook whether can we implement semaphore with no busy waiting. So try to look the answer. It is yes, but there will be an explanation on this. Next, we look into semaphore implementation with no busy waiting. Just now for this question, we try to look into how we're going to implement this semaphore in our busy waiting. With each semaphore, there is an associated waiting queue. Each enter a waiting queue for 2 data items, which is value and pointer. For the 2 operation, which is block and wake up. So you have the waiting for 2 data item, value and pointer, and in terms of 2 operation, block and wake up. So maybe you can try to do exercise 4 after I share you the example for example 1 and example 2. It is not too hard, which is quite to the example. How you going to apply the semiphora. Later on, you can see also there is a example. Just now, you learn on producer and consumer. Still remember producer and consumer? And there is several other exercise you can try too. Okay, let's take a look into next subtopic. We're going to look into deadlock and starvation. This one is not, I guess, not a new term for you. About deadlock, when deadlock will be occurred. Let's see the example of deadlock first. Okay, let's see the example of deadlock first. And about the starvation. Okay, about the deadlock and also starvation. Deadlock, 2 or more processes are waiting. And starvation indicate indefined blocking. So I give you example of deadlock. Let's say we have this junction. I cannot draw car properly. Okay, this car want to go here. This car want to go here. And there is a car want to go in front. And there is a car want to go opposite way. So if you can see there is a lot of car. It is very traffic. There is traffic jam here. So this one need to wait car in front to move. Here also need to wait. So there will be a correlation waiting for each other. So 2 or more processes are waiting in defining for an event that caused by one of waiting process. So it's called a deadlock. So this car A wait a car B to move first. So it's need to wait. So this car C maybe need to wait another car in front, car D, to move first, then it can move. So it is a waiting that event that this car D to move. So it is under deadlock. And starvation is defined on the blocking. A process may never be removed from semiphora queue in which it is a suspend. So you're going to see, let's say in a semiphora just now, if someone having if there is some process in the CS, so what you need to do for P1, you need to just wait. So it is going to come out with the starvation because you cannot even suspend it. Okay, you cannot, process cannot be removed. So we can summarize it. Mutual exclusion, prevent deadlock, maintain the test and set, wait, signal, and semiphora. We take a look into that. Synchronize process using a hardware and software mechanism. So that is only in our chapter 6. I guess it is just about you need to know all these where is it? All this theory in terms of algorithm, patterns and solutions, synchronization hardware, mutex log, and semiphora. As long as you can differentiate between each other, you can answer the question I just saw. Okay? So next class, we're going to go deeper in our chapter module 7. So try to take a look into this module 6. I will record a video for example 1 and example 2 for you to refer. Okay? Any question?
Doctor, so since our test got delayed, so is there any change of syllabus which were included in the test too?
No changing in the syllabus. It is just in terms of the date.
Okay.
Okay, if there is no question, we will end our class. And for the rest who join late, you can scan the QR code. Where is the QR code? Okay, there. Then for others, you can left and we meet again in our next class with our module 7. Thank you and stay safe. Bye bye.
Thank you, Doctor.
Thank
Thank you,
you.
Doctor.
Thank you.